Okay, so here are some video solutions for the 2022 EC312 12-week exam. The first question here is asking you to look at a CAN setup. So we have 4 CAN nodes, 20, 21, 22, and 23. Those are the only things we should see in the ID portion of the CAN message. Connected to a 500 kilobit per second CAN bus, each of the nodes set up with the configuration shown to the right. So we're assuming that each CAN node has its number there. It's connected to a motor B with max speed of 2,000 RPMs, a motor A with max speed of 5,000 RPMs, and then that's on PWM out pin 0, PWM out pin 1, and then we have digital pins D0 through D7 connected to a display here that is set up to do roughly the same thing as we did in the lab on digital logic. So this is the one where we have these segments that correspond to an LED input that represents a digit. And so that's all going to be important for the future problems here, just describing what's happening, because this entire question is really just asking you to explain what happens based on the CAN messages that you're seeing. So we use those digital out pins to display the displays. Active high, meaning a logic 1 causes the segment to light up. And the input of this would cause the segment to display 3, and we can sort of do that just by drawing out D01, D02, D03, D04, not D05, not D06, and D07. So we can see that that makes a 3 here. So that's how we'll use that diagram later on in the problem. So moving on, it says for the PWM outputs, digital analog conversion factor from decimal value to PWM percentage is 100 over 255. So that's max value 255, and then multiplied by 100 to get us percent. And then it says for each of the following cases, determine what the outcome would be observed. Your answer should take the form of node blank motor blank turns at blank RPM, or node blank display lights up with decimal number blank. Show all work. So we're expected to translate this CAN message and data and understand what happens either on the display or on the motor, depending on what the message is. I'm going to go ahead and pop up another window that zooms in on the CAN tables just so we can reference those for the rest of the problem. So the first problem is part A. A node transmits a CAN message with ID 216 and 1 byte of data 0x60. So for the ID, we want to break that into first, OX216, convert that to binary, and we'll get 0010 for 2, 0001 for 1, and 0110 4 plus 2 for 6. If we look at the message format for CAN, and this is in the table at the top of the page now, it's zoomed in here on the screen, we can see that we have a 7-bit node ID starting from the right, and then a 4-bit message prefix. So let's just sort of section off 7 bits. So we've got 1, 2, 3, 4, 5, 6, 7. That's going to be that portion of it is our node ID. And then the next 4 bits are the message prefix. So we can just look in that table, reference the 4-bit values that are there, and scan through the table. We find that 0100, which is what we have for our message prefix. Don't get confused because it's 2, which would be 0010. That might correspond to timestamp in the message prefix up there, but we're shifting over by 1 here in the binary since it's a 7-bit node ID. So 0100 is our message prefix, and if we look at the table, that corresponds to 0100 prefix corresponds to RPD01 as the message format. And if we look across the table at what that corresponds to, that RPD01 corresponds to digital out. So that's what our message is being sent for. We also need to translate that node ID, and there we're just going to take that hex that we have for 7 bits. So we're still going to have a 6 at the end, but we're going to have a 1. So OX16 in hex is going to convert to 16 plus 6, which is 22. So that's our node is 22. And so we can start writing our message here. Because it's a digital out, We know that digital out pins affect the display, not the motor. And we can see that from the diagram here. So digital out pins go to the display. And so we can start writing out our message, which is node 22 display lights up with decimal number. And we don't actually have the decimal number yet, so we need to do a little bit more work there. We still need to fill in that blank. It says that our 1 byte of data here is OX60. So let's go ahead and say OX60 in binary is 0110, and then D is corresponding to 13. So 1101 is what we're going to get for that. And now we need to figure out what that looks like on the display. So keeping in mind that this is D0 here over to D7, that's how our outputs look. We're going to have the D0 pin, and at this point I'm going to follow. I'm going to just scroll down a little bit here so we can see this diagram. So I'm just following that rightmost diagram that shows the 7-segment display, or the 8-segment display. And I'm just going to fill in the lines that correspond to D0 through D1. So D0 is not on. That's always 0 in this case. So D1 is on. D2 is on. D3 is not on, so we're not making that line. D4 is on, so we are making this line at the bottom. D5 is on, so we're making that line. D6 is not on, D7 is on. And so we can see the number that we get out of this, which is displays digital number 2. And that's it for that problem. We've been able to write out the whole message, so let's go ahead and move on to the second one. So problem number 2 here is a node transmits a CAN message of ID OX317 and 8 bytes of data OX3300, FF00, and then zeros the rest of the way across. So let's go ahead and figure out what this is. We're going to do the same process. So OX317, and that gets translated to binary of 0011, 0001, 0111. Okay, we're going to group the 7 bits, so count 4 bits and then 3 more. That's our node ID. So OX17 is going to be our node ID, which is going to turn into 7 plus 16, which is 23. So our node is 23. And then the rest of this, we look at the table that we had up before, and I'll scroll back up to that. And so if we look at that table, the prefix of 0110, keep in mind, again, it's just those 4 bits. We're shifted over by 1 from the binary we translated. So 0110 is going to be RPD02, which if we follow that to the right-hand side, it's going to be PWM out. So this is data coming over the PWM channel, which from our diagram of the setup is going to be going to the motor. And so, again, what the problem had told us to do was sort of write out a message saying node 23 motor turns at blank RPM. So we now need to figure out what RPM this is going at. And so let's figure out what we have here. And we might actually have 2 of these because we have, you can see in our data, we have 2 values that are non-zero. So keeping in mind that this stuff gets translated in little endian order, we're going to have that motor number for PWM. It's listed as PWM out 0 to 3, so it's similar to the digital outputs, that it's going to be the 0th one first. So this is PWM 0, this is PWM 1, and then the rest of them are 0. So we're going to have 2 outputs, so we can say that node 23 motor turns at motor blank turns at something RPM. We can fill this in now where we can say motor 0 and motor 1, or motor A and motor B, sorry, is what they have in the problem. So motor A and motor B. Motor A is connected to PWM pin 0. Motor B is connected to PWM pin 1. So motor A turns at blank RPM, motor B turns at blank RPM. Let's take those pieces of data. So we'll have OX0033 is the first one, and OX00FF. We've got to convert those from hex to decimal. This one's fairly easy, so we'll say this is 255, and then we'll have 3 times 16 plus 3, so that's going to be 51, and so that's that. Sorry, just double checking myself to make sure I got that conversion correct. It's harder with my computer out of the way here. So yeah, 51. And then we do the conversion based on the factor that we were given in the problem, which is to take 51 times 100 over 255, and that gives us roughly 20%. And then this one, 255 times 100 over 255 is going to give us 100%. So we should have 100% of the RPMs for motor B and 20% of the RPMs for motor A. And then if we just look at those values, we should see that motor B is going to go at 200 or 2,000 RPMs. So 100% for B is going to be 2,000. And for motor A, 20% of 5,000 is going to be roughly 1,000 RPMs. Okay, and so that's it. That's all we're sending out for that message. That's the whole thing. So then part C, this is getting into the cyber attack that we looked at in reference to CAN. So it says a node attempts to transmit the message from part A at exactly the same time as another node attempts to transmit the message from part B. And this is really just a which one is going to win. So we've got part A's message is OX216, and B is OX317, and we're trying to decide which one of these is going to win. And so we know based on what CAN does is that arbitration goes with the node or the message prefix first, and then the node ID second. And in both of those cases, lower equals higher priority. So we know that if we're transmitting both of these at the same time, we're going to have OX216 wins because that message prefix is going to be based on 0010 instead of 0011. So this is going to have a lower message prefix. That means it's going to win out. So OX216 wins arbitration. And that means, given that this asked us to give the output in this specific format, we're going to say that node 22 display lights up with decimal number 2. Right? Because that's what happened in part A. And so if A's message wins, that's what's going to happen, physically on these micromod boards. Okay, so that's it for problem 1. Let's look at problem 2 very quickly here, and we're using the same problem setup here, so it's worth just looking at immediately. And here it says, suppose node 23 gets hacked and starts flooding the CAN bus with RPD02 messages in a denial of service attack. Circle all that will be impacted by the attack. Indicate which equipment will no longer be controllable due to the DOS attack. So this sort of follows from part C that we just solved. And that's following the fact that lower numbers get higher priority. And so we'll have to figure out, what might be impacted by this particular message. And so node 23 is sending RPD02 messages. And that means that it's only going to win against other things that are using RPD02 or lower on the chain of command here. So the RPD01s are all going to be okay. So the 7 segment displays are all going to win out over the RPD02 messages because those are RPD01. Those have a higher prefix, so they're going to win arbitration. So the question is, what else might sort of lose out here? And compared to node 23, again, lower is going to be higher priority. So anything with a lower number then 23 is also going to win out in arbitration. So node 21 wins for both motors, node 22 wins for both motors, and then the only thing that's left is node 24. So node 24 has a lower node ID than node 23. That means it's going to lose out, and it's going to lose out for both motors because of the fact that it has, this lower node ID. It doesn't really matter which motor. So the key concept there is that the data doesn't really matter. It just matters what the node ID and the message prefix are, because that's all that goes into arbitration. The data that's being sent doesn't actually come into play here. So that's it for problem 1 and 2.